Assalamu alaikum. Welcome back, students. Now we are going to start the lecture number 2 of the thermodynamics. Last time we were studying some basic concept of the thermodynamics. Now from today, our new topic is it's all about the processes and the cycle. Last time I told you about the state. State is basically a set of fixed properties, and whenever there is a change in any property, the state will change. So what is process? Simply, process is any change that a system undergoes from one equilibrium state to another. So, with the help of process, the state will change from one point to another point. With the process, we have to define another term which is called path. Path is basically the series of the states through which a system passes during a process. So, the path can be different, but we have to define the state number 1 and state number 2. Like we have to define the initial and the final states for a complete process. So whenever we have to describe a process completely, there should be the initial and the final states, as well as we have to define the path and the interaction with the surrounding. Here in this example or in this figure, you can see we have the state number 1 here, and this is the state number 2. We have two different states, and this is the path. So path can be different. Like if I have to move from state 1 to state 2, I can go from here, I can go from here to here as well, or I can use this path as well. So whatever the path you are going to follow, the result will be different. So we need a process to change a system from one state to another state. We have different type of processes, but this one is the ideal process, which is called quasi-equilibrium process. It is basically an ideal system, an ideal process, and it doesn't exist in real life. Quasi-equilibrium process is defined as when a process proceeds in such a manner that the system remains close to an equilibrium state at all the times. Means the system is moving very slowly so that the equilibrium is maintained at all times, which is not possible in real life. Otherwise, if you have to move from one point to another point, then you will take a year to move from one point to another point. Now, whenever we have the processes, we normally show the process on a process diagram. Normally, you have already seen some process diagrams. You have seen a PV diagram when you were drawing the Carnot cycle in your second year. So here, some common properties that are used as coordinates are temperature, pressure, and volume or specific volume. You can use the volume or you can use the specific volume, and these are the diagrams. So you can see this is a process diagram on a PV diagram. So this is basically y-axis and this is your x-axis. So we have a P and V. This is called PV diagram, and we have this initial state here and the final state here. So normally it is a piston cylinder device which is moving from this point to this point. So it's moving from here to here, and this is the initial one and this is the final one, and this is the path that the system is following from point number 1 to point number 2. Now we have different type of processes. The process can be isothermal, it can be isobaric process, it can be isochoric process. Isothermal process means that the temperature remains constant throughout the process. For the isobaric, the pressure will remain constant, and for the isochoric, the specific volume or the volume will remain constant. There are so many other processes as well. There are so many processes. These are some few examples, like we have the isothermal, isobaric, isochoric. I think you should know about the adiabatic process as well, where there is no heat transfer. But in the real life, we have different processes, and we have to define the path that the process is following. Now, here we have a steady flow process. Normally, when we are talking about this steady means constant with respect to time. The term steady implies no change with time. The opposite of steady is basically unsteady or transient process. So normally we use the steady, unsteady. So steady means whenever there is no change with respect to time. So what is a steady flow process? A process during which a fluid flows through a controlled volume steadily. Means if the fluid is passing through a system and at a location, you can see here we have a mass in and this is mass out. This is basically an open system. This is mass in, mass out. So this is at 1 p.m. So here at 1 p.m. at this point the temperature is 300 degrees Celsius, and at the outlet you can see the temperature is 150 degrees Celsius. Now with respect to time, this is 1 p.m. Now the time is changed and this is now 3 p.m. but still you can see the temperature here is same as here. So there is no change in the temperature with respect to time at a point. Remember, it is basically at a point, at a given point. So at a given point, there is no change in the property with respect to time. So 300, 300, 200 here. You can see 200 here at the outlet, 150 degrees Celsius. Here you can see 150 degrees Celsius. So with respect to time, there is no change at a given point. So it is called steady flow process. So what will be the unsteady? Unsteady is if there is a change in the property with respect to time. So we have the steady process, we have unsteady process. A large number of engineering devices operates for long periods of time under same conditions, and they are classified as steady flow devices. So it is very easy for us to classify different devices as steady flow devices, and then we can easily say that with respect to time at a given location the property will be same. So steady flow condition can be closely approximated by devices that are intended for continuous operation such as turbine, pumps, boiler, condenser and heat exchanger. And even for refrigeration system we define as the steady flow process. So this is all about the steady flow process when there is no change with respect to time at a given point. We also define one more flow process which is called uniform flow process. It is basically uniform flow process, and the definition for the uniform flow process is if there is no change in the property with respect to location, not with respect to time. If there is no change in the fluid property with respect to location, then it will be uniform flow. For the uniform flow, if I'm taking the same example, so if the water is coming from here at 300 degrees Celsius, so it should be 300 degrees Celsius here because we're talking with respect to location and should be 300 degrees Celsius here. So if there is no change with respect to location, then it will be called uniform flow. So uniform flow is basically with respect to location, while the steady flow process is with respect to time. So please don't confuse. So here we have under steady flow condition, the mass and the energy contents of the control volume remains constant. Where it is steady flow, so the mass in should be equal to mass out. So for this control volume or the open system, the mass in will be equal to mass out. So the energy and the mass of the control system, of the control volume will remain constant. So we have steady flow process, we have isothermal process, we have isochoric, isobaric, adiabatic process, and then we have real life processes as well. We will discuss about other processes in chapter 4. Now, again, some basic. We have a zeroth law of the thermodynamic. You know about the first law of thermodynamic, that energy neither be created nor be destroyed, or in other words, the total energy of the system and surrounding remains constant. But here we have zeroth law of thermodynamics. The zeroth law of thermodynamics simply states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. So if we have three bodies, let's suppose we have A, B and C. We have three different bodies and the temperature of A and B is same and the temperature of B and C is same, then it means the temperature of A and C will be same. This is this zeroth law is basically used to calibrate the what you can say the thermodynamic scales. So normally if I have a thermometer and I'm going to check the temperature of myself and showing that I have a temperature of, let's suppose, 99 degree, and any other body have the same temperature on the same thermometer, because the thermometer is showing the same reading for me and for that body. So we have a body which is myself, which is body A, we have thermometer which is body B, and we have another body which is body C. If the thermometer is showing the same reading for me and the other body, so it's mean the temperature of my body and the other body is same. So by replacing the third body with a thermometer, the zeroth law can be restated as the two bodies are in thermal equilibrium if both have the same temperature reading, if they are not in contact. If they are not in contact, so my body and the other body is not in contact, but still because the thermometer is showing the same reading, so we have the same temperature. Now the temperature scales, we already know about two temperature scales, even three temperature scales. We know about the Celsius, we know about the Fahrenheit, even we know about the Kelvin scale as well. So normally all temperature scales are based on some easily reproducible states such as freezing and boiling points of water, that is the ice point and the steam point. Normally if we have the pressure of 1 atm, 1 atmospheric pressure, then a mixture of ice and water that is in equilibrium with air saturated with vapor at 1 atmospheric pressure will be at 0 degrees Celsius or 32 Fahrenheit. So ice point is basically 0 degrees Celsius or 32 Fahrenheit at 1 atm, 1 atm pressure. If the pressure is changed, then the ice point will be different. Same for 1 atm pressure, the steam point is 100 degrees Celsius or 212 Fahrenheit. So steam point is 100 degrees Celsius at 1 atm pressure, 1 atmosphere pressure. So normally all temperature scales are based on some easily reproducible states. So we have ice point, we have steam points for our scales. So we normally define, you can see you know about these terms. We have Celsius scale in SI unit system. We have Fahrenheit scale in English unit system. Then we have thermodynamics temperature scale. A temperature scale that is independent of the properties of any substance. So any temperature scale that is independent of the properties of any substance is called thermodynamic temperature scale. And we have two thermodynamics temperature scale. We have Kelvin scale in SI and we have Rankine scale in English unit system. You know about the Kelvin, so there is one more scale which is Rankine scale. So the unit conversion is simply, we have the Kelvin scale is simply the temperature in Celsius plus 273.15, and for Rankine is simply the temperature in Fahrenheit plus 459.67. So simply, if you have to find the temperature in Kelvin, so simply you have to add 273.15 in temperature in terms of Celsius scale, and if the temperature is given in Fahrenheit, then you have to add 459.67 to get the Rankine scale temperature. Normally when we are talking about the change in the temperature, so change in the Kelvin temperature will be same as we have the change in the temperature for Celsius scale. Same as if we have the delta T for Rankine, so it will be equal to delta T for Fahrenheit as well. So remember, the change in the temperature for Kelvin is equal to the change in the temperature for Celsius, and the change in the temperature for Rankine is equal to the change in the Fahrenheit. And remember one thing, for the Celsius scale, for the Fahrenheit scale, and for the and this for these two, we have to use the symbol of degree. But when we are talking about the temperature in Kelvin or Rankine, then we are not using any degree sign. You can see here we have the Fahrenheit, so degree sign here for Celsius, but for Kelvin and Rankine we don't have any degree sign. So please be careful for this thing. Now we have temperature scales. Next property, and this is the most important property for thermodynamics. We have temperature and we have the pressure, and these two properties are interlinked with each other. What is pressure? Basic definition of pressure is simply the force per unit area. So any normal force exerted by a fluid per unit area, it is called a pressure. So normally the force per unit area, so it will be Newton per meter square. Newton per meter square. Force upon area is simply Newton per meter square, and normally we can say that the 1 Newton per meter square is equal to 1 Pascal as well. We have different units for the pressure. Different units for the pressure. Okay, for here you can see we have two different persons having a 70 kg of weight mass, and the second one having a 140 kg of the mass. If you can see, the area of the feet is basically 343 centimeters square. Now if I'm going to check the pressure on the area somewhere here, so it will be equal to the mass times the 9.81. So we have the weight, which is equal to force divided by this area, and again here this is mass times 9.81 to get the weight, which is equal to force divided by this area. So here the force is higher, so you will get the higher pressure. We have half of the mass, so you are going to get the half of the pressure that you are getting here. So simply mass times 9.81 to get the weight, which is equal to force divided by area, and then you will get the pressure at the bottom. So this is a simple way to calculate the pressure. Now as I told you, we have different units. So here we have different units and their equivalency with each other. We normally use the bar pressure as well. We use Pascal, we use atmospheric pressure, even we use torr, even we use millimeter of Hg. So normally 1 bar is equal to 10 power 5 Pascal or 100 kilopascal. So 1 bar is 100 kilopascal, while 1 atmosphere is equal to 101.325 Pascal. 101.325 Pascal or 1.01325 bar. 101.325 Pascal or 1.01325 bar, or in term of torr, so we have 760 torr and even 760 millimeter of Hg for 1 atm. So we have different conversion for the pressure. Normally we will use in term of Pascal, atmosphere and bar. And sometimes we can use in term of millimeter of Hg as well. Now when we are talking about the pressure, we have different types of pressure. We have different types of pressure. The first pressure is atmospheric pressure. Simply the pressure exerted by the atmosphere. Right now we are standing or we are sitting somewhere, and from the top of our head to the top layer of the ozone there is some atmosphere, there is air, and air has mass, air has some weight as well. So the pressure exerted by that air or that atmosphere is equal to atmosphere pressure. Second one is the absolute pressure. Absolute pressure is basically the actual pressure at a given position. It is basically made relative to the absolute vacuum or absolute zero pressure. So we have the absolute pressure, which is the actual pressure at a given position. And we have one more pressure which is called gauge pressure. Sometimes we have the pressure which is above the atmospheric pressure, So the extra pressure will be called the gauge pressure. In any case, if there is a pressure which is above the atmospheric pressure, it is called gauge pressure. And the total pressure or the absolute pressure will be the atmospheric pressure plus gauge pressure. The atmospheric pressure plus gauge pressure will be the absolute pressure, because the absolute pressure is the actual pressure at a given position. Normally, most pressure measuring devices are calibrated to read 0 in the atmosphere, and so they indicate gauge pressure. Probably you have checked that if you are going to fill the CNG or the air in your in the tires of your car, then it's going to read as 0 pressure when there is no gas. So it's basically 0 gauge. It's basically 0 gauge, not the 0 absolute, because there is some atmospheric pressure as well. So actual pressure is basically atmospheric pressure plus gauge pressure. So the pressure measuring devices will read the gauge pressure. So you have to add the atmospheric pressure to get the absolute pressure. Now, if there is a pressure drop and the pressure is below than the atmospheric pressure, then it is called vacuum pressure. It is called vacuum pressure. In this case, the absolute pressure will be atmospheric pressure minus vacuum pressure. So the absolute pressure is simply the atmospheric pressure minus vacuum pressure. So you can see here we have absolute vacuum, which is P absolute somewhere here, P absolute 0. So this is our reference line. So this is relative to absolute vacuum. So absolute vacuum is basically in space because there is no atmosphere. So from here, from this black line, if we're moving up, so we are somewhere here where we are experiencing some atmospheric pressure. So this dotted line is basically the atmospheric pressure. So this one is atmospheric pressure exerted by the atmosphere. Now, any pressure which is above the atmospheric pressure is called gauge pressure, and the absolute pressure for this case will be P atmosphere plus P gauge. So P atmosphere plus P gauge is P absolute. Or in case of the vacuum pressure, so pressure will be below the atmospheric pressure. So you can see we have less pressure than the atmospheric pressure. So in this case, absolute pressure, which is here, is equal to atmosphere pressure minus P vacuum. P atmosphere minus P vacuum, or in other words, P gauge is equal to P absolute minus P atmosphere, or P vacuum is equal to P atmosphere P absolute minus P absolute, or in both cases P absolute is equal to P atmosphere plus P gauge or P atmosphere minus P vacuum. Here we have a simple question. You can see we have a vacuum gauge connected to a chamber, reads 40 kilopascal at a location where the atmospheric pressure is 100 kilopascal. Determine the absolute pressure in chamber. We have to find the absolute pressure, and the vacuum gauge is connected and it is reading 40 kilopascal. So we have vacuum pressure of 40 kilopascal, while we have the atmospheric pressure of 100 kilopascal. In this case we have in this case we have atmospheric pressure of 100 kilopascal and the vacuum pressure of 40 kilopascal. So absolute pressure will be equal to 60 kilopascal. Simply P atmosphere minus P vacuum equal to P absolute. In this question, if I'm going to only rub this one, if I'm going to remove this word, a vacuum, so it will be a gauge connected to chamber reads 40 kilopascal. If it is not mentioned that it is a vacuum gauge, then the gauge will read gauge pressure. For that case, the absolute pressure will be 100 plus 40 kilopascal, which will be equal to P absolute equal to P atmosphere plus P gauge, and you will get 140 kilopascal. So be careful and please check either you are getting the vacuum gauge or only gauge. Gauge will read the gauge pressure while vacuum gauge will read the vacuum pressure. Now we have four different type of pressures. We have atmospheric pressure, we have gauge pressure, we have vacuum pressure, and then finally we have an absolute pressure, which is the actual pressure. Now normally when we're talking about the pressure varies with depth. Normally what we say, at the sea level we are going to experience the value of pressure equal to 1 atmosphere. At the sea level, the atmospheric pressure is equal to 1 atmosphere. Now what will happen if we are moving up or down from a reference point? If I'm going up, so it means the amount of the atmosphere on top of me will reduce. So the pressure will reduce if I'm going upside, or pressure will decrease if I'm going up from a reference point. While if I'm going down from a reference point, then pressure will increase because the amount of the air or amount of the fluid will change, and the pressure will increase if I'm going downside from a reference point. So you have to remember that if we are moving upside, then the pressure will decrease, and if we are moving downside, pressure will increase, but on the same level for the same fluid, the pressure will remains same. So here the pressure of a fluid at rest increases with depth as a result of added weight. So pressure will increase if you're moving downside. So here you can see this is a level. Normally we use this symbol for the top surface of the water or any fluid. So it's means if we're going downside from this point, so pressure will increase. So pressure is going to increase, and this increase is basically equal to rho g delta z, means how much depth you are covering from here to here. So delta p means from this pressure to this pressure, it will be equal to rho g delta z, or if I'm going to combine this rho g, so I can say that it's equal to gamma, which is specific weight, times delta z. So rho g delta z or rho g h height, or gamma h or gamma delta z is equal to the change in the pressure if we are moving downside or upside. For the downside, it will be positive, negative, and then if we are going upside, then it will be again positive and negative. So only thing is to remember that if we are moving top side, the pressure will decrease. If you're moving downside, the pressure will increase. So here, simple. If I have the pressure here, which is equal to P atmosphere, somewhere here on the top side. So atmosphere pressure is here, and then we have plus rho GH due to this one. So plus rho GH, and then you will get the pressure. Sometimes the P atmosphere is not given. In any case, if atmosphere pressure is not given, then what we do, we simply move this one P atmosphere from here and we subtract from here. So this is P, then it will be P minus P atmosphere equal to rho GH. So P is basically absolute pressure minus P atmosphere, so it will become gauge pressure. Absolute minus atmosphere is equal to gauge pressure. So this pressure is basically equal to gauge pressure, which is equal to rho GH. So rho GH is normally the gauge pressure. So here you can see at point number 1 we have atmosphere pressure, at point number 2 we have simply P atmosphere, and we are moving down from point 1. So we have to add the pressure. So P atmosphere plus rho GH equal to P2. If I am going to solve this one from here to here, if this is my point 1 and this is my point 2, so it will be P1 minus rho GH equal to P2. So remember your reference point, and then remember that either you are going up or down. If you are going down, then you have to add the pressure, and if you are going up, then you have to decrease the pressure. So pressure in a liquid at rest increases linearly with distance from the free surface. So this is one point that you have to remember. The second point is, in any case, if we are checking the pressure variation and we are using the gases instead of liquid, we are using gases, then in the case of gas, the pressure variation with respect to depth can be neglected. We can easily neglect the pressure difference for gases with respect to depth, because we have the formula for the pressure which is equal to rho GH. So the density of the gases are very low. Normally the density of the air is 1.2 something, while the density of the water is 1000. So you can see the difference. We have the density of the air which is 1. So the delta P in case of water and in case of air for the same depth will be 1000 times less if we are going to use the gas. So in a room filled with a gas, the variation of the pressure with height is negligible. So for the gases, we will neglect the pressure difference with respect to depth. And one more thing that we have to remember, you can see here we have different shapes here. So you can see the different shapes for this container. But if I'm going to check the pressure here at point A, if I'm going to check the pressure here at point B, at point C, point D, point E, point F, and point G, these all points are at the same level for this fluid. So for any fluid at the same level, the pressure will be same. So PA equal to PB equal to PC equal to PD equal to PE, PF, PG. So for same liquid at the same level, the pressure will be same. So the pressure is the same at all points on a horizontal plane in a given fluid, regardless of the geometry, provided that the points are interconnected by the same fluid. So by the same fluid, the pressure will be same at different points on the same level. So remember this thing. So we have two things that we have, we have three things that we have to remember: that the pressure will be same for a same liquid at the same level, horizontal level, while the pressure in a liquid will change, will increase if we are going downside, or it will decrease if we are going upside from a reference point. And the for gases, we normally neglect the pressure variation with respect to height. So we have to remember all this point. Now We have another law which is called Pascal law. This is also related to the pressures. So pressure applied to a confined fluid increases the pressure throughout by the same amount. So here we have to check that we have a confined fluid. So if it is not a confined fluid, then you will not get the Pascal law. And remember that the pressure is same, not the force. And the pressure is always normal. Remember, it is a normal force per unit area. So sorry, in the previous example, if you can see here, at point A, point B, point C, so you can see we have the pressure in normal directions. So again, it is always at an angle of 90 degree. So you can see here we have a confined fluid here, we have a container, and we have a confined fluid. For the Pascal law, normally we say it is a liquid rather than gas, because in the gas the variation is very low. So normally we use the liquid. So liquid is confined in this container. You can see here we have a container here, and this is point number 1 and this is point number 2. I'm going to apply a force on this piston. So it will be, the force is basically sorry, the pressure is simply force upon area, so force will be the pressure times the area. So pressure times the area is force. So if I'm going to apply a force here, so this force will create a pressure here, and the same pressure will be exerted here on that piston. But because the area is larger than this one, you will get higher force. You will get higher force. You are applying low force and you are getting more force. Because according to the Pascal law, the pressure at point 1 and point 2 is same. So pressure here and the pressure here is same. So if the pressure are the same, so pressure is force upon area. So F1 upon A1 is equal to F2 upon A2. So you will get more force at higher or more diameter or more area. So with the help of this one, we can build different hydraulic jacks, hydraulic brakes, even hydraulic lifts as well. So these are all due to Pascal law. So we have defined the pressure, we have checked the different type of pressures, and then we have the Pascal law. Then we have next topic, which is measurement of the pressure. Now, if we have the pressure, then we have to check, or we have to measure the pressure as well. So first thing is the measurement of the atmospheric pressure. For the atmospheric pressure, we normally use barometer. We normally use a barometer, which is a device used to measure the atmospheric pressure, and the construction is very simple. This is the barometer. Normally we have a container here. It is filled with a known fluid, a fluid which density is given. Normally we use a fluid having higher density. In the case of mercury, we have a density of 13600, which is very much higher than water. So normally we use mercury in order to get the atmospheric pressure. We can use water, but then this height this height will be large enough, and you cannot manage that height. Right now, if I'm going to use the mercury here in this container, so what we will do, I will insert a tube here, test tube here. So the atmospheric pressure will act somewhere here, and we will get a vapor pressure somewhere here. And now we will get an equilibrium state. Vapor pressure is equal to the atmospheric pressure, and we will get this height. This height will show the atmospheric pressure. This height will show the atmospheric pressure. And how we can get the atmospheric pressure? Simply we have the formula of the pressure is equal to rho g h. We have the h value, we have the rho value, which is 13600 for mercury, and then we have g value, which is 9.81. So rho g h, and then you can get what is the atmospheric pressure. So here, this one is the atmospheric pressure, which is equal to rho g or gamma h. So we know what is the rho for the mercury, D value is 9.81, and H is normally in this case you will get around 760 millimeter if you are at sea level. At sea level you will get 760 millimeter. That's why we normally say that the 1 atmosphere is equal to 760 millimeter of Hg. But if you are going to use the water, then the density of the water is 1000 times 9.81 and equal to P atmosphere, which is equal to 11325 Pascal. Then you can get a much higher value of this column, and you will around get I think you will get around 10 meter or more than 10 meter, which is not suitable to use the water to find out the atmospheric pressure. You can find out easily if the atmospheric pressure is, let's suppose, 101,325 atmospheric pressure and rho gh, and we have rho of 1000 times 9.81, then you can easily check what is the height if you are going to use water, and in that case the height will be much higher, and it is not recommended to use the water. Normally what we do, we use a fluid having higher density value. In this way we can calculate the atmospheric pressure, but still we have to find the gauge pressure as well. So what we do, we use manometers. Normally the manometer is a device that is used to find the pressure with the help of simple concept that we have a pressure, simply the concept that the pressure will change with respect to height. So pressure measurement devices based on the use of the liquid column in vertical or inclined tubes are called manometers. So manometers will use the concept of P is equal to rho gh, and the pressure is going to increase if you're going downside, and the pressure will go will decrease if you're going upside. So you have to remember these 2 points. So mercury barometer that we use to find out the atmospheric pressure is one of the type of the manometer, because we normally use the same concept to find out the pressure. Now we have different type of manometers. We have piezometer tube, we have U tube, and we have the inclined tube manometers. The piezometer tube is the simple one. So this is the piezometer tube. So piezometer tube is simply a vertical tube open at the top and attached to a container or a pipe in which the pressure is desired. So here we have the container here, which is this one, and we have a pipe. We normally insert this pipe and we connect with this container or the vessel. We have a liquid or we have a fluid here. This fluid will exert a pressure. This fluid will exert a pressure while while from this end, which is the open end, the atmospheric pressure will act. So we have the atmospheric pressure somewhere here at the open end, and we have the pressure of the fluid from inside. So at one point these two pressure will be in equilibrium state, and you will get a height. Now with this height you can check or you can calculate the pressure inside this tank. Simply we have the pressure here, which is P atmosphere. So P atmosphere is exerting at this surface, and we have to check the pressure here. So basically we are going downside, so it will be P atmosphere plus, because we are going downside, and it will be plus rho gh up to this point. So P atmosphere plus rho gh. You can check again here. We have piezometer. This is a container at point A. We have to find the pressure, and we have the open end here. So here we have the P atmosphere. Here we have the PA, and this is the height. So if I'm going down from here to here, I can easily find out the pressure at point A. So if I'm going to write the equation, so it will be P naught plus, because I'm going down, so it will be P naught plus, if I'm going down, if I'm going downside, so it's basically going to increase, so it's plus gamma or rho g, and then we have h, which is height. So we have P naught plus gamma H, and it is equal to the pressure somewhere here. But for this liquid, we are at the same level, so pressure here is equal to pressure here. So we have the pressures at this point and the pressure here at point number A is equal. So I can easily write the PA absolute is equal to P naught plus gamma H. So the gamma is basically rho g. So we should know the density or the specific weight of the liquid or fluid that we are going to fill here. So we can rearrange. So if I'm going to rearrange this one, so it will be PA minus P naught. In any case, if atmospheric pressure is not given, please do not assume any value. Please do not assume any value. Rather, simply solve PA minus P naught. Now, this PA is basically P absolute minus this P naught, which is the atmospheric pressure, and you can easily get PA minus P naught, and this one will be equal to gauge pressure. Now, you can easily write PA gauge. So, the gauge pressure will be equal to gamma H. So the pressure at point A is simply equal to rho gh or gamma H. And in any case, if you know what is the atmospheric pressure, then you can simply add to get the absolute pressure. Now remember, there are some disadvantages to use the piezometer. Normally, the piezometers cannot use to measure the gas pressure. We cannot measure the gas pressure with the help of piezometer. If we have the gas in this container, so the gas pressure is very less than the atmospheric pressure, then there is a chance that this liquid will go inside this container. So it is not used to measure the gas pressure. Now, second is it cannot measure the high pressure so that the required height of the tube is reasonable. If we have the high pressure in the container, then this height will be much more high, and which is not feasible. The last one is it cannot measure negative pressure, otherwise air will be sucked in. So again, this is same as we have the gas pressure. If we have the negative pressure here and we have the higher pressure, then all the gas will go inside. Remember that the fluid will flow from higher pressure to low pressure. The fluid always flow from higher pressure to low pressure. So this is the piezometer, which is the first type. Now we have second type. This type is called U-tube manometer. This is basically modified form of the piezometer. To avoid the disadvantages of the piezometer, we use the U-tube manometer at the same concept, but here instead of going straight in that type, we're using the shape of U. You can see here we have a U-shaped manometer. So U-tube manometer is a U-shaped tube, contains a fluid in it called gauge fluid. The gauge fluid must be immiscible with other fluids in contact with it. Normally, the two common gauge fluids are water and mercury. Again, the concept is same. We have to move from one open end or from this end. If this is my reference point, so here we have the pre-atmosphere and we are going down, down, down. So the pressure will increase. On the same level, we will jump from here to here because we have the mercury here, we have the mercury here, and then we are moving up. So pressure will decrease and then we have the same level. In this way, we can write the equation and then we can solve or we can calculate the pressure in the container. Right now you can see here. So here we have height from atmospheric pressure to point number 3. From point number 3 to point number 2, the pressure will be same because we have a gauge fluid, and in the same liquid at the same level the pressure will be same. So we have P atmosphere at the top surface, we have the P atmosphere somewhere here, and then we are going down So it will be P8 atmosphere plus, because we are going down, plus rho gh up to this point, and then we are moving from here to here, because the pressure here will be same here, the pressure here, and then we have to move up and we have to reach here. So when I'm going up, so it will be minus of rho gh up to this point, and then the pressure at point A, sorry, at point 1 will be equal to the pressure at point A, because we have the same level for this fluid. The pressure here will be equal to the pressure here. Here you can see this one, the new height, and we have the PA. So if I'm going to write the equation, so it will be P atmosphere plus rho gh for this fluid, which is rho gh2 up to here, and then jump from here to here, and then going up. So it will be negative of rho gh1 equal to PA. Then I can rearrange this equation, and then it will be equal to, simply I'm going to rearrange in a way, because I don't know the atmosphere pressure, so it will be PA minus P atmosphere, so it will be gauge pressure, so it will be rho g h2 minus rho g h1. So this is h2 and this is h1, and in this way I can get what is the PA. Okay, if the fluid in the container is a gas, then the fluid one term can be ignored. In this way, you can, the equation will be simply rho to h2, because the P atmosphere plus rho to h2, the pressure here will be equal to the same pressure here, and for this one, because we have the gas here, in the gas cases, the variation with respect to height is negligible. Now when we will solve the numerical in next class, then it will be easy to understand, but remember the points that for any fluid at the same level, the pressure will be same, and if you are going up, the pressure will decrease, and if you're going down, the pressure will increase. Now we have these things I have already discussed, that in the same fluid we can jump across from 2 to 3 as they are at the same level, and thus must have the same pressure. The fluid in the U-tip is known as the gauge fluid. The gauge fluid type depends on the application, that is the pressures attained, and whether the fluid made is a gas or liquid. Now we have another type which is called the inclined tube manometer. So this is the inclined tube manometer. We have a pipe or vessel A, and we have another pipe or vessel B, and they are connected with each other with the help of an inclined tube manometer. Normally, inclined tube manometers are used when the pressure difference in these two pipes are very small. In order to get the small pressure variation, we use the inclined tube manometers. Again, the concept is same. We have to use the vertical height rather than this inclined length. In this case, length is given, the theta is given. We can easily calculate what is the height here, the vertical height. So remember, we have to use the vertical height in the formula P is equal to rho gh. In P is equal to rho gh, we have the vertical height and there is no inclined length. So we have three different type of manometers. We have a barometer, then we have piezometer, U-tube manometer, and then we have the inclined tube manometers. In the case of U-tube manometers, sometimes we will have the multi-fluid manometers. We will do this thing in numericals. Okay, for this class, I think it's enough for today. Inshallah, for the next class, we will do some numericals, and then this is the end of chapter 1. Inshallah, we will do some numericals.